In this video, we're going to continue to look at the energetics of water. And first, we're just going to look at the types of interactions that are in biochemistry in general. And really, weak interactions drive biochemistry. And so, what do I mean by weak interactions? Well, a strong interaction would be covalent bonds. And a covalent bond have very high bond energies in the hundreds of kilojoules. Weak interaction would be your non-covalent interactions, such as your ionic interactions, van der Waals interactions, hydrogen bonds, dipole-dipole, London dispersion interactions. These have much weaker bond energies. And if dipole-dipole, ionic, London dispersion, if those don't really ring any bells for you, those were covered in general chemistry, but please let me know and I'll be happy to go more into depth with you on those. If we just look at what these interactions mean in general, dipoles, interaction between permanent dipoles, you have two molecules that are always partially charged. They will orient themselves to interact negative and positive. You can take a permanent dipole, put it next to a molecule that does not have a permanent dipole, and that second molecule will orient itself so it has partial positive interacting with partial negative. And if you put two molecules together that are nonpolar, what they will actually do is that they will orient their electrons in such a way that you have one molecule having more electrons on one side interacting with the second molecule that does not have electrons on this side. And these arrows, the size of these arrows, are showing you the strength of the interactions. Where permanent dipoles are the strongest type of interaction, such as in a hydrogen bond, dipole-dipole interaction, versus London dispersion interactions, incredibly weak, break all the time. And the way we measure these interactions is through Coulomb's law, where the energy equals K, a constant, multiplied by the charges of your molecules, divided by dielectric. Dielectric is a constant for each type of solvent. The more polar the solvent, the higher the number. And also divided by the distance of molecules, which we call R. So this is basically saying that two charged molecules of opposite charge have a stronger interaction than things that are just polar. Here, negative energy is good, so you want this term to be negative. And that is Coulomb's law. Again, we'll do some practice with that in class. Now, for water, we have a term of like dissolves like. That is, things that are hydrophilic or water-loving dissolve in water. And hydrophilic molecules are polar. So water is polar, hydrophilic molecules are polar, they dissolve each other. Hydrophobic molecules or water-fearing are nonpolar. They do not dissolve in water. And the reason why polar molecules will dissolve in water is because water will surround these molecules. So here we have sodium and chlorine. Table salt. Table salt dissolves in water very easily because the water molecules will form a hydration shell around the sodium where all the oxygens point at the sodium, and it'll form a hydration shell around the negative chlorine where all the hydrogens point towards the chlorine. And when this happens, we say that the molecules are now solvated or hydrated, and you can have multiple layers of water surrounding the ions like this, and each layer is called a hydration shell. But it doesn't just have to be ions. Here I'm showing we have an oxygen molecule connected to something else. That's what the R is. R is anything else. You can see that water can interact like that. Here we have a carboxyl group interacting with water. Here another carboxylic acid interacting with water, and an amide interacting with water as well. And note that one of the things we have to be aware of in biochemistry when it comes to energy, if we want, for example, carboxylic acid and this NH3 group to interact, we have to remove all of these water molecules first. We have to remove the hydration shell. And higher levels of biochemistry, this is a very big issue that you have to consider when you do calculations. At this level of biochemistry, we really don't have to take that into consideration, but it is something we should be aware of, these hydration shells and the need to remove hydration shells. Now, what happens if we put a nonpolar molecule into water? In the previous slide, we looked at polar. Well, in a nonpolar molecule in water, water cannot hydrogen bond to nonpolar molecules. Therefore, water does not want to interact with nonpolar molecules, so they're going to minimize the interaction with hydrophobic molecules. Basically, water forms a cage. That's what's being shown here, and groups all the nonpolar molecules together. And this is called the hydrophobic effect. And if you ever dropped oil into water, or have seen that happen, initially, if you drop different droplets of oil into water, they will eventually be grouped together. Because when they are grouped together, the amount of water molecules that have to interact with that oil has been lowered. Because the water molecules surrounding this oil or nonpolar, they're very ordered. They aren't moving. They form this cage. So entropy has gone down by forming this cage. But by doing that, all of the other water molecules in this solution do not have to interact with this nonpolar substance, so they are free to hydrogen bond. So few water molecules make that sacrifice for the greater good. And if you actually look at the energetics of the hydrophobic effect, so let's take something that's hydrophobic in water, and imagine if you go and you could pick up the hydrophobic molecule from water and place it in a hydrophobic solute. So taking something from water and putting it in benzene, and you measure the energetics of that. What you'll see is that delta G for this is negative, so this is spontaneous. The nonpolar molecules will go to the nonpolar solvents. But interestingly, the enthalpy for this is positive. That is, it's actually, in terms of enthalpy, it's favorable for the nonpolar molecules to be dissolved in water. But if you talk about entropy, it is unfavorable for these molecules to be dissolved in water. And this is because water forms the cages. So not only is the water ordered, but the molecules inside that cage aren't free to go wherever they want to go. So they are also ordered as well. So by transferring a nonpolar molecule from water to a nonpolar medium, you are creating more chaos. So chaos is driving this process, or entropy is driving this process. Now, inside the cell, you really don't have that many molecules that are strictly hydrophobic, because in the cell you don't want these giant clusters of hydrophobic molecules. Rather, you have molecules that are amphiphilic or amphipathic. What that means is that these molecules contain both nonpolar segments and polar segments. Fatty acids being your classic example, or lipids, where we have just a long chain of nonpolar carbons in a polar head group. And inside water, what they will form are micelles, where you have the polar head group pointing towards the water and the tails are buried. Or you can form bilayers, which is basically just two micelles combined. And when you have this, you have water that can hydrogen bond with the head group, so energetically this is much more favorable. And what's being shown here is an actual real picture of a micelle. So it might not be as neat as it's drawn here. This is the real image of it, where the reds are oxygen and the gray is all carbon. So this is what a real micelle looks like. Now, speaking of water and energetics of water, we can look at the diffusion of water, because this idea is very important, as cells are full of water and cells are also full of dissolved things, dissolved particles. And this leads us to the idea of collective properties. Again, something that was covered in general chemistry. Collective properties are simply physical properties of a solution that are affected by dissolving materials in that solution. So, for example, if you put salt in water, you're going to increase the boiling point, decrease the freezing point, and increase osmotic pressure. And for us, what really matters inside the cell is osmotic pressure. And if you look at a simple experiment, if you have a solution with water and solute in that water, what will happen is that water will flow into that solvent to try and balance out the concentrations. So water flows from high concentration to low concentration. And the differences of these pressures is called osmotic pressure. Inside red blood cells, this is extremely important, because if you have a red blood cell, the outside of that red blood cell must have the same concentration of dissolved things. That's called an isotonic solution. If you don't, if you put red blood cells into a solution that is more concentrated, water will leave and the red blood cell will shrivel. While if you take red blood cells and put them into a solution that is just pure water, water will rush into the red blood cells and your blood cells will pop. So this is very important, especially when it comes to hospitals and injecting fluids into people. So animal cells really don't have any protection through osmosis or osmotic pressure. Plants and bacteria have some protection. They have cell walls, which help to reduce the effects of osmotic pressure. And with osmotic pressure and osmosis, scientists have learned to take advantage of this phenomenon. In a very simple lab experiment that takes place, it's called dialysis. So let's say you are trying to purify these blue beads from these red beads. Well, what you can do is you can have a membrane that allows the diffusion of red beads but not blue beads, and you put this tube inside water. What will happen is that the red will naturally go from high concentration to low concentration. And you can do this a couple times, and eventually you will have no red beads left. So this is used in biochemistry for purification and for switching salt solutions. Let's say that you have a protein and a solvent with one salt, and you want to switch it with another salt. You can do this through dialysis, where your solution you're putting it in has your choice of salt that you want to switch. That's it for this video, and I will see you in the next video.